Hello students, here I am discussing some special reactions from Friedal-Crafts acylation reaction. In last video I discussed some exceptional reactions and special reactions from Friedal-Crafts alkylation reaction. Okay, so here about the Friedal-Crafts acylation reaction, some special reactions. Okay, so here the first one is the major product formed in the given reactions. Okay, so actually here the acylation reaction. Okay, so here benzene on reaction with the acid halide, the presence of anhydrous Lewis acid, for suppose here AlCl3, here by some bond formation between non-bonding electrons from the chlorine and to the vacant orbitals of the aluminum. Here by the bond formation between the aluminum chlorine, this bond becomes weaker and here completely break down. So as a result we will get the acylium ion and AlCl4 minus. So here alkophile is generated in this manner. This one attacks on the benzene. So it is a alkophil substitution reaction. It is nothing but a Friedal-Crafts acylation reaction. Okay. So here in this case, what is the A and what is the B? Here benzene on reaction with the pyvoloyl chloride. What is the pyvoloyl chloride? So pyvoloyl chloride is this one, CH3 here, this one CH3 and CH3, C double bond O Cl. Okay, if you take acylating agent like CH3COCl in the presence of the Lewis acid AlCl3, here just a simple acylation takes place. H replaced by the COCH3. That is the alkophil substitution reaction. But here in this case, this is a pyvoloyl chloride. This one on reaction with the AlCl3. So first here initially by loss of Cl minus with the AlCl3, that gives a acylium ion. Okay, acylium ion. This one. Okay. Of course, it is stabilized by the resonance. It is stabilized by the resonance like CH3 here, CH3 and CH3. The C triple bond O here plus. Okay, but here in this case the adjacent is a tertiary alkyl group. By breakdown of this bond we will get the stable cation like here CH3 here CH3 and the CH3 plus and here CO carbon monoxide. There is a leaving of the carbon monoxide because here there is a chance for the formation of the stable cation tertiary butyl. Okay, but here in this case if it is a methyl or if it is a phenyl, there is no chance for the breakdown of the acylium ion. Okay, because this methyl cation and phenyl cation are less stable, but in this case tertiary butyl carbocation, so there is a breakdown of the acylium ion. So as a result in this reaction, instead of the acylation, alkylation takes place, that tertiary butyl acting as a alkophile. So here that attacks on the benzene, H replaced by this tertiary butyl group. Here only alkylation takes place instead of the acylation reaction. Okay, that's it. And next here the same pyvoloyl chloride on reaction with the anisole. Here actually that anisole is more reactive. This anisole is a more reactive. So here there is a ready attack of the alkophile takes place. In this reaction acylation takes place at the ortho position. That means here as usual acylation takes place in this reaction. Okay, because here anisole is a more reactive. As soon as alkophile is formed, that is attacked by the electron rich benzene ring of the anisole. But in this case here benzene less reactive when compared to anisole. Here there is no ready attack of the benzene and acylium ion. So in that duration, that is dissociated into stable cation and stable molecule carbon dioxide. Okay, that's it. So it is a one interesting reaction. Okay, here alkylation takes place even if you take a acylating agent. Okay, here acylation takes place. First suppose here in this case next the major product of the reaction. Here you know that already Friedal-Crafts alkylation and acylation reaction. Okay, so you can see some exceptional reactions from Friedal-Crafts alkylation reactions. I have given description in a description the link about the Friedal-Crafts alkylation reactions. Okay, you can see that video also. So in this case there is a alkyl group, that means here alkyl halide and the acid halides are there. So here there is a chance for the alkylation as well as acylation. That means here if it is a here if this Cl minus is leaving with the AlCl Lewis acid, this is the alkylophile actually. Okay, this is the alkylophile. Now here if this Cl minus is leaving, this is the alkylophile, C double bond O plus. But here between these two, which is the more stable? This is the more stable cation actually. That means here more stable actophile, because it is stabilized by the resonance. That means here that is stabilized by the lone pair of electrons from the oxygen. Okay, that's it. So here in this case this cation is less stable because it is a withdrawing group. There is a partial negative charge here, partial positive charge repel each other, so it is destabilized by the positive repulsions. Okay, here in this case this cation is stabilized. So here the Cl from the acid halide is readily removed. So here in this case here acylation is more favorable. That the product is B actually. The major product formed in this reaction is the B. And next here, this acetic anhydride. In acylation, actually, we can use a carboxylic acids, acid anhydrides, and acid halides. So this acid anhydride in the presence of AlCl3. So here in this case, by breakdown of this group, we can get this acylium ion. That means here, this one, or by breaking down of this group, we can get the mixture of electrophiles CH3CH2. But here which is a more favorable, which electrophile, which carbocation is more stable? This carbocation is a more stable one, because here the positively charged carbon is more stabilized by the strong plus side group. Here methyl is a weak plus side group and ethyl is a strong plus side group. So in this case here there is a more chance for the formation of this electrophile. So in this case the major product is this one. So this alkylophile attacks on the benzene that can replace the H plus. Okay. So here in this case here we have two chances, but here methyl is a weaker plus side group, here ethyl is a strong plus side group, so that stabilize this cation actually. Okay. That's why here in this case we will get the ethyl phenyl ketone as a major product. And next yeah, one more interesting reaction here, this one I have taken from the Clayden and Jonathan Clayden and Greaves water. So in this case, the major product are formed in the reaction actually. So of course, you know that actually the benzene having electron withdrawing group are not involved in a Friedal-Crafts acylation as well as alkylation reaction. But here in this case, acetophenone and here acetic anhydride is there. Okay. So actually here in this case, this product is not formed and this product is not formed, this product is not formed. Of course it is not a ortho-para directing, it is a meta directing actually, but here the substitution is not on the benzene ring. It is a very interesting reaction. Okay, you can see why, because this one form a Lewis acid base complex. So here in the presence of the BF3 Lewis acid, here enolization is enhanced. Okay, the rate of enolization is increased. So here OH double bond, here CH2. Now here in this case actually, of course here by writing the resonant structures for this one, here double bond O, here H plus, here CH2 minus. That means here this terminal carbon is a more nucleophilic, so this nucleophilic carbon attacks on this alkylophilic carbon actually. So here in this case acylation takes place on this side chain, that is nothing but methyl. Here acylation on the benzene is not possible in this case. So here finally the product is this one, D. That means here is a nucleophilic carbon. This nucleophilic carbon attacks on the positively charged carbon. This is okay, and then complete leaving of this group. So here this is the major product. Okay, that's it. Of course, it is nothing but a active methylene group that is blank between the two strong electron withdrawing group. Okay. Of course, this compound has a higher enol content, more than 90%. This compound has a enol percentage. Now next one more reaction. In which of the following reactions phenanthrene is a product? Okay, so here what is the structure of this phenanthrene? Here phenanthrene structure is this one. Okay, that also has a three benzene rings actually. Okay, so if three benzene rings are continuously present, that is anthracene. So here in this case, in which case phenanthracene is a product. Okay, it is actually naphthalene, and this is a succinic anhydride. So here by the acylation of this anthracene, sorry, naphthalene. Okay, first here acylation takes place on this one. Okay, here C double bond O, here CH2, here CH2, C double bond O, OH. Okay, of course here by loose acid base complex formation, here alkophile is generated, thus alkophile attacks on this one. Okay, so here for naphthalene, here most preferable position for the alkophile attacking is 1. So initially alkophile attacks are this one. By the multiple steps we will get this one. Now here next one, by reaction of zinc mercury and HCl, at the Clemmensen reduction, we know that CO is converted to CH2, and next here on reaction with the SOCl2, this is converted to acid halide, and then reaction with the AlCl3, intramolecular acylation reaction takes place. This intramolecular acylation at the ortho to this carbon. So here the product is benzene, here benzene CH2, CH2C, this one double bond O. Now again here zinc mercury HCl, there is also Clemmensen reduction again. So as a result of the Clemmensen reduction, we will get this product. Now it is saturated ring, so it is oxidized by the palladium carbon. That means here there is a loss of hydrogens. Dehydrogenation takes place. As a result, finally we will get the phenanthracene as a major product in this reaction. So here option is mostly this one. So here the same procedure if applied on this reaction, we will get the anthracene actually. We will get the anthracene product. Now here in this case, actually CH2Br. So here benzene on reaction with first of all Br minus leaving with AlCl3, a substitution takes place. We will get the CH2Br. Similarly, another molecule is formed, CH2Br. So here in this case again, alkyl substitution at this position, alkyl substitution at this position. So in the presence of AlCl3, so here we'll get the benzene CH2, here benzene. Okay, now here this one on reaction with palladium carbon, here totally it is dehydrogenated, so it is oxidized. Okay, it is oxidized to the actually anthracene. Okay, this pi 1 here pi 1 pi 1. Okay, this is the dehydrogenation, nothing but aromatization. Here aromatization mostly done by heating with palladium carbon, or heating with sulfur, or heating with selenium also. Okay, remember this one. Next here in this case also same, here this benzyl chloride, two molecules of the benzyl chloride, here CH2 plus alkophile is generated first, and this CH2 plus alkophile attacks on the ortho position of another benzyl chloride. Okay, so here initially we'll get this product CH2, and here this is benzene. So here CH2Cl, again another time Friedal-Crafts acylation alkylation takes place. So here in this case CH2, here CH2, followed by aromatization we will get the anthracene. So here finally the product phenanthracene is formed in option 1. And next here finally one more reaction, one more interesting question. The feasible reaction is regarding the acylation of the benzene on benzene nucleus. So you know that nitrobenzene is not involved in the Friedal-Crafts alkylation as well as acylation. Okay, not only if nitrobenzene, that strong electron withdrawing groups like NH3 plus, CF3, and CCl3, CHO, and CN or benzoic acid. Okay, all these are not involved in a Friedal-Crafts alkylation and acylation reaction because of the deactivation of this benzene ring by these strong electron withdrawing groups. Okay, next here, so here nitrobenzene is not involved in a Friedal-Crafts alkylation and acylation reaction. Here this reaction is not feasible. Okay, that's it. But now here this reaction is feasible because here alkoxyl substitution, if this one, if Cl combines with the LCl3, will get the this alkophile. This alkophile cannot attack on the nitrobenzene. So that means here the substitution on the benzene of the nitrobenzene is not possible. But here in this case, substitution on the benzene, okay, Here the alkylophile is this one. So after formation of the alkylophile, that can attacks on the simple benzene. So the interesting one product is this one. So NO2 C double bond O benzene. Okay, this reaction is a feasible reaction. Next here, chlorobenzene and acylation reaction. Of course here chlorine is a even a deactivating group, that is a ortho para directing group. So this is the major product. Of course in a halobenzene so always that para isomer is the major product. Of course we can get the ortho isomer also. Okay, that's it. Next here in this case okay, see reaction of this reaction also feasible. Now here in this case pyridine in field of acylation is not involved. Okay, you know that alanine is not involved in the field of alkylation acylation because of the Lewis acid base complex formation. By Lewis acid base complex formation, that becomes a NH2 plus AlCl3 minus. That means here it is that nitrogen becomes a positively charged nitrogen, so it is a strong electron withdrawing group. That's why here no further reaction. That means here by coordinating by bond formation with AlCl3, that ring is deactivated. Here also same story is applied. This nitrogen non-bonding electrons form a bond with the AlCl3, so substitution is not possible. AlCl3 here minus, here plus, that means here positive charge of nitrogen highly deactivate the ring, so here for the substitution is not possible. So here pyridine also not involved in a field of alkylation reaction or acylation reaction like aniline. Okay, that's it. Thank you for watching. Please subscribe my channel for more videos which are very useful for JEE advanced exam. If you like the video, share to your friends. Thank you.